All right. Thank you. Thank you, Alma. So welcome, everyone. This is the very first talk for our seminar series, the Good Engineering Seminars. And I'm really excited to have every one of you here, and hopefully more people will trickle in. But our series today starts with TG's talk. TG is Thamme Gowda, and he'll be presenting to us PyTorch 101. He himself is a established PyTorch practitioner. I'll quickly read his bio for you guys who don't know him. Thamme Gowda is a research programmer at ISI MDR. TG obtained his MS and CS from USC, and he's currently pursuing a part-time PhD. He's a passionate programmer with 7 years of programming experience. He's been using PyTorch for the last 3 years, and he's the primary developer of a PyTorch-based toolkit called Reader Translator Generator, RTG. Awesome. TG, thank you for joining us and doing this today. And I turn it over to you to take it further.
Thank you, Joel, and thanks for the introduction. Thanks everyone for joining. It's a cloudy morning in Marina del Rey, and for some of you it may be afternoon. Okay, so let's get started. I hope everyone can see my slides and hear me. So PyTorch is, I'm not going to waste a lot of time, talking about how PyTorch is great, etc., etc. So I just asked, I had asked, I have sent a form asking for what do you like to hear, and thanks everyone who filled out that form. I received some really useful pointers, and I took most of them, and I'm going to walk through or answer some of the questions that was sent in the form, in the Google form. So we will go through this list one by one as we progress. So this talk is designed to answer most of these questions. We will go through the one by one. So one of the question, almost all of the audience are familiar with Python. Some of them are new to Python. So in the past session, we gave it, we offered some advice on best practices on Python if someone is new to Python. If anybody is new, I strongly recommend checking this out, this link. I will be sharing these slides later in the Slack channel, and you will have all the links. So just remember that there is another document that talks mainly on PyTorch best practices. And here in this talk, we will be focusing mostly on PyTorch. Okay, so another question I received was, I want to know how to install PyTorch on Windows, or what are the best practices for installing PyTorch. I recommend using Conda environments. Conda comes in two flavors. One is Conda distribution, and other one is mini Conda. So use mini Conda. It's light, it's easy to install. If you go to this link, when Conda is available for Windows, Mac OS, and Linux, you can download one of these links and then install it. For example, for Windows, you have .exe file, you can download and run it, and that installs Conda. Once Conda is installed, it's really easy to install PyTorch. So PyTorch also has a nice UI for, to help you install or customize for your environment. If you open PyTorch get started link, you can choose what is your operating system, how do you like to install it, and do you want GPU support or not, and you just copy paste this command and PyTorch is installed. So the best part of using Conda is it works the same between operating systems. For example, you're using Windows laptop and then you want to install it again on the Linux server, so the command is the same. So it works same across the environments. And so you can use Conda to manage environment, but also you can use pip to install PyTorch. PyTorch comes with two other useful libraries like Torch Vision and Torch Text. If you are working on Vision, you have Torch Vision that comes with some data sets, and you are working on NLP. Torch Text library gives you some ready-to-use data sets. In fact, in this talk, we'll be using Torch Text. So another response or feedback I got was, show me your tools, or what kind of tools are you using for PyTorch, or what tools help make your life as a programmer easy. So I hope everybody is using Git, and I use Git to track all the ideas in parallel, like create branches and then work on ideas in parallel. Then I strongly recommend using PyCharm IDE for development. It's great for debugging. So in PyTorch, we'll be working with higher dimensional tensors. Sometimes you do want to, you want to look inside the tensor and see, is the mask working properly? Is in place updates or anything inside the tensor, is this position currently updated? So PyTorch gives you that kind of debugging tools. And if you want to take documentation, I'm using AsciiDoc. For example, this website is wholly generated using AsciiDoc. And so it's just useful to take notes of any experiments or any features I'm working on, and they just become documentation like this, so you can share it with your team members. I use Emacs to work on remote machines. If you're a Vim user, Vim is also fine. I use Tmux. So I have active Tmux sessions. I just log in and attach to the sessions. And so Tmux is very helpful. I strongly recommend using Tmux if you're not already. Then I use HTOP to monitor CPU and RAM utilization. I should be able to show HTOP actually. So yep, it shows HTOP. Then I use GPU stat to monitor GPU utilization. It's really useful tool. It shows you GPU and RAM, CPU utilization, etc., etc. And it can also run in interactive mode. Let's say you want to update it every 5 seconds. So it shows you how active, how busy or free the GPU is. I use TQDM to monitor the training progress. I use TensorBoard. We will be talking about TQDM and TensorBoard later. And I also use Slurm to run my training in parallel. I create Slurm batch scripts and then submit to the cluster, and cluster runs it whenever the GPUs are available. So more useful tools, if anybody wanted to listen or use, for me, it's really helpful to organize directory structures based on projects and experiments. And this is a useful trick I learned from one of my team members. I think John May or somebody else showed me how to do it, which is you can create a history file in a directory. So when you go to a directory, your history file, all the commands you ran in that directory is stored there. So that way, because I already organized directories based on my projects and experiments, the commands I ran for that particular experiment in particular project is stored inside that directory. So I strongly recommend using history based on your directories. So let's say you want to rerun your commands or your experiments later, in 3 months later. So your history file sitting in the directory will be right there. Okay, so next topic or question I received is, what are some common pitfalls that may lead to proper but slower training? How to efficiently use resources such as CPU and GPU? Okay, so this is a hard question. So first thing first is monitor the utilization using HTOP, how much CPU is utilized, how much, and the GPU stat, how much GPU is utilized. And if the GPU is not pushed to 90 to 100%, then there is a room for improvement. So GPU is a expensive resource. You may want to make best use of it. So Sometimes the answer could be, if the GPU is underutilized, then you may want to fit, it may be possible to fit bigger batches, especially if GPU RAM, if you have some more GPU RAM left, you can increase the batch size. Now GPU is pushed to the limits. Other time, so that would be the one easy solution, but most of the time the solution won't be that easy. So let's say you observe that GPU is not fully utilized, but CPU is fully utilized. So CPU percentage, sometimes you see 100% or 200%, depending on how many threads you are using. So the key thing is, it means some of the code that you're running on CPU need to be parallelized on GPU. So all the GPU code would use torch.api. So behind this torch API, they have written GPU accelerator code. So instead of running a for loop, things like for loop runs on CPU, can you express the same logic? Can you achieve the same outcome using PyTorch API? So recommendation is use PyTorch API as much as possible, because this torch.apis knows how to parallelize on GPUs. Then another use case would be, sometimes not everything can be parallelized on GPU. So you may want to increase more threads on CPU. If you are using Slurm, so this is some pitfall I fell into, which is, so Slurm has strong CPU affinity. So you may request, I need to run 10 threads. That's different than you may request n equal to 10, I need to run 10 tasks. That's different than running one task with 10 CPU cores. So Slurm has this check. If you said you're gonna run 10 tasks, then the default option for C is 1. So it will restrict just for one CPU. Whereas explicitly specifying how many CPU cores I want, Slurm would allow you to use all the 10 CPU cores. So the next thing is, if both GPU and CPU are free, meaning none of them are 100% utilized. So then you would start to wonder, why is it slow? Possibly because the disk you have, the disk you have stored your training data may be slow. That's why CPU is not able to work fastly, and neither is the GPU. So usually when you're on a shared compute grids, we will have network file storage, and which the the disk is utilized by many people in parallel. If the disk is slow, then the whole training process becomes slow. So this is something to watch for. So the solution is, can we copy training data from a slower disk to a faster disk? So usually these nodes provide some local disk that is fast, often SSDs. So this could be one solution. When you run your job on a node in a cluster, just copy the data to a faster disk. Other option is, maybe sometimes you have plenty of RAM, you can fit everything, all the data into CPU RAM. So then just do it. So you don't have any disk IO. All the training data is in RAM. Sometimes it's possible, especially when you're working with low resource data sets. So then even much harder problem is when you are writing PyTorch code is out of memory or memory leak. So sometimes you expect the memory to be free, but for whatever reason, garbage collector is not working and memory is not freed. So this is really, really the nightmare. But once you understand how things work, then you won't fall into these pitfalls. So just basics. Garbage collector is the one that is in charge of deleting unused objects from the memory, right? So garbage collector try to figure out, is this object still used or not used? And the way it figures is there a reference to this memory or not? So if your code is keeping hold of references to the objects in the memory, garbage collector won't be able to delete it because it thinks you're still going to use it. So the recommendation is always, if you're done with, say, batch object, then get rid of the reference to the batch. So don't add it to a list or hold some temporary variable or any other variable that reference to that batch. So it works out of the box. You don't have, we are not writing C++ code where we have to manage our own deallocation. So it works. You just have to be careful that don't hold references to the objects you don't want. And PyTorch API makes it so nice that you forget that underlying our code, the graphs are being built. So that often, because we don't see it, we often make some mistakes. Most of our code underlying has a computation graph. Sometimes it's good to detach the graph. For example, you have a loss and you have a total loss. You make current loss, you add the current loss to the total loss. What if the loss itself is a node from the graph? Just because you added it, now this whole graph is now having the total loss is having reference to this whole graph. So use tensor.detach when you don't want to hold references, and use lazy loading instead of eager loading. For example, in Python 3, this little thing can make a big difference in terms of memory. So these are some common pitfalls, and then some more issues for advanced users to consider is Python has limitations like multi-threading. So if you out of the box, it's only one thread. And we use multi-processing. We try to create more processes. So underlying Python takes a pickle dump of your object, then again loads it. So if the object you're dumping and loading is too heavy, say you're dumping and loading the whole training data multiple times, then this can be slow. So try to be careful whenever you're thinking of multiprocessing. Think of, okay, Python is going to dump this object and then load it again, serialize it and deserialize it. And so try to keep those objects light. And okay, I'm going to skip some of these. And just keep in mind that an integer in Python, in the basic Python, is 28 bytes. It's not 4 bytes. And floating point is 24 bytes. So if you have a list of integers in Python, in pure Python, each item in Python list is going to take 36 bytes. It's 28 bytes for an integer object, then 8 bytes for the pointer to the integer object. So this is why we should instead use NumPy or Torch, because here you have the control. So these are arrays, and this takes, you can control it. Say I want 4-byte integer, then the integer is going to take 4 bytes. So early on, even in the data processing, if you're using pure Python list, if you can swap them with NumPy or Torch, then it would be a great improvement in terms of memory. Okay, so now let's get some more deeper into PyTorch. So these are all general advice. So I had asked in the form how many of you are familiar with NumPy, and I think most of us are familiar with NumPy. Let's see. So this was a form. Most of us are familiar with NumPy. So if you see 54% of my audience have used NumPy for some basic stuff, and then there are more advanced users. Only a small portion have never used NumPy, so which is great. So the good news is, if you know NumPy, then PyTorch is going to sound very native to you or familiar to you, because PyTorch, the API is just like NumPy API. Plus, they have added more extra stuff for deep learning. So NumPy doesn't work on GPUs out of the box. PyTorch works on GPUs out of the box, and we need auto gradients for backpropagation, and some extra utilities like loss functions, optimizers, and commonly used neural network modules like convolution networks, transformers, RNNs, etc., is part of PyTorch. So if you are at the beginner of NumPy, but you want to know more of NumPy, so there is a cheat sheet. If you click on this link, so there is a sheet that tells you all the things you want to know about NumPy. So these things, once you know NumPy, PyTorch is going to sound a lot familiar to you, because instead of NumPy.squared, you would be doing torch.squared. Instead of array, you would be doing NumPy.array, you would be doing torch.tensor. So this will, instead of d type equal to float, you would be doing d type equal to torch.float, something like that. So I recommend becoming a pro in NumPy, because it's going to help you, one, for PyTorch. Also, if you might want to do some visualization like matplotlib, NumPy is going to help there. And in fact, most of us have used NumPy because whenever we want to do matplotlib or some visualization, we need it. Or we want to use scikit-learn or SciPy, we need NumPy. So If you're already there, then PyTorch is going to sound a lot familiar to you. And other question is PyTorch functional API or object-oriented API? Some of us have, we are inclined towards one or the other. I personally incline towards object-oriented API, but I also use functional API when it feels fit. So PyTorch gives both the API. PyTorch is mostly object-oriented, but it also has functional API for those who want to use functional. And the import, for example, you import nn.functional as f, and then we can call f.anything or torch.the function. So it also gives object-oriented version of it if you want to use it. So you might use, instead of functional.crossentropy, you might use nn.crossentropy object, the class. So, or instead of torch.max and passing tensor to it, you also have an option tensor dot on that object you can call the function. So it has both the variations. Documents cross-reference each other. I'll show you docs soon. So another thing I want to emphasize is some of the functions end with underscore. So as I mentioned before, under the hood, PyTorch will be building a graph, and the behavior of these functions, for example, scatter that ends with underscore versus scatter that does not end with underscore, these two have different behavior on graph. So I recommend using the one without underscore for a beginning. Then the one with underscore are in-place operations. So they can be damaging. Sometimes they can introduce bugs. So use underscore only when you know what you're doing. Otherwise, just use the one without underscore. And again, PyTorch will give you both the variation. Do you want in-place operation, or do you want out-of-place operation? Okay, so that's a quick overview of PyTorch API. Let's, oops, sorry, sorry, I pressed something and it skipped the slides. Okay, so we were here. Okay, so another thing to remember is now you also have another decision to make, because PyTorch code works on CPU as well as GPU. By default, you want your code to run on CPU or GPU. So I suggest prefer to run your code on GPU. If GPU is not available, make it on CPU. So I suggest making your code work on both of them, because some of us, we will use a laptop that does not have a GPU, and we want to use an IDE like PyCharm to debug the code. So running on CPU helps us debug the code, but making it run on GPU helps us run it on our servers where GPUs are available. So this is the template that everyone uses, which is, if CUDA is available, then the default device is CUDA, which is a GPU, else fall back to CPU. So one thing I strongly, one thing I discourage is do not hard code a specific GPU. So your machine may have 4 or 5 GPU, do not hard code it in the code here saying CUDA 2. Instead, let the environment variable take care of it. So hard coding this code, hard coding things like CUDA 2 or CUDA 4 make it less portable. So remember to leave that choice to environment variable called CUDA visible devices. So here, when you use CUDA and the environment variable is set to 2, it will automatically pick the device 2. Okay. So now, okay. Now let's focus on end-to-end examples. Sorry, let's see if there are any questions I can answer. Okay, so we will answer all the, okay, we'll answer these questions in the end. They're really good questions. Okay, so let's focus on, the slides will be available. Sure, I will make these slides available. In fact, there's a link in the end. I will post this link in the end. And I also have a SPatch configuration. It's linked in the last slide. And How do you measure GPU utilization? Sure, GPU utilization is, I usually measure it here in, I have a tool called GPU stat. You can install it on using pip install GPU stat. And if GPU is utilized, it shows what percentage of GPU is utilized and how much RAM is utilized. Okay, let's continue with the end-to-end example. Okay, so to make an example, we need to refer to PyTorch docs, and this is the website. You need to keep it open because all the documentation is available right here. Any function we're going to use, this is where we come and look up, let's say, a scatter function. So we search for it, and then we will, tensor.scatter. So we go here, and then it tells us out of place version of scatter. So now it's cross-referencing to scatter function. So here is the full documentation and with an example. So these examples really helpful to understand how this function behaves. We will keep this website open in case you want to write code. So because I need to show an end-to-end example, I picked a task which is text classification. Most of the responses I received, audience said we work with text data, so I am using a text classification as an example. For the thing about NLP is data processing itself takes a whole hour. Unfortunately, I can't spend all the details of preparing the data set for this end-to-end example. So I'm going to short circuit as much as possible. I'm going to use torch text to retrieve the data set and then go to the key part, which is how do you track the training, how to visualize the training. I might not even go in depth to the transformer encoder because that's again itself takes an hour to describe how the transformer works. So I will short circuit as much as possible, but I'm trying to give you things that you can use in your code, regardless of what problem you're trying to solve or what model you're trying to use. So things like TQDM and TensorBoard are really useful. Okay, so let's so the data set I'm going to use is, I use a library called torch text. You can import, it comes with a lot of data sets. You can open this link and then see what data sets are available. In fact, there are so many data sets. If you're working on NLP, these data sets are already prepared for you. So I tried these data sets, and the AG News is the one that is small enough. So I'm using AG News. So it comes with the training and validation set. All you have to do is just run this. And let's see if it runs. It should run. Okay, good. So yes, so now we have data set, which comes in training and validation set. In your problem, you may want to implement your own custom data set. But here I'm short circuiting because that itself takes an hour. So next step you need is a data loader. Now we have a data set. The next step is how are we going to make batches? We need to make random batches. So that is shuffle equal to true. So PyTorch gives this class called data loader. This is what we're going to use for loading data. It takes certain arguments like our data set and shuffle equal to true, which shuffles the data set between every epochs. Then it also takes batch size. We can control how big our batch is, and collate function. So this is, we take each examples and then separate them into, we need to make them as two separate tensors. One of them is an X tensor, that's our input, and another one is the Y tensor, that's our labels. So we need to make them as tensors. Currently, the data does not come as two big tensors. Here, we are going to make them collect them as separate list. But how are we going to make this? How is it possible to make this as tensors? So if you look at labels are easy. It's just an array. Whereas if you look at text come in unequal lengths. So we have sequences with, say, 35, sequence 1 is 35 tokens, other one is 45 tokens. We need to fit them into one tensor. So how we do it is, we have in our vocabulary, we use something called padding index. And so this padding, sorry, so okay, we have in our vocabulary, we have an index, we have an item called padding. So we create a tensor such that it's, the extra space are padded. So we create a tensor. So, okay, sorry, let me walk slowly. So we create a tensor for labels. It's easy to create a tensor. We can specify data types and we compute the length. And then we create another tensor with the number of sentences and then the maximum length. And then we load, we fill that tensor. It's called torch.full with the value padding index. So this whole tensor is filled with padding. Then we go through our text and then load the beginning portion of each row with the whatever text we have. Okay, so now this is unique to NLP, is that we need to keep track of padding. Unlike images, they may all come in the same size. So okay, I hope this is clear that why we're dealing with padding. So another thing is we need to now keep track of lengths, because we need to know which of these tokens are padded and etc. So okay, so in production, I would write code something like this. I take that code and I would write it in an API like this, which is I create a class called batch. It takes text and then labels and then lengths. These are all tensors. Then the collate function is here. I pass that as a argument to data loader. The nice part of creating this API instead of just doing the crude way is this can be easily modified. So you can add some extra functions like what's the length, how many tokens are in this batch, which is going to be useful for computing the speed. And then you can easily move this to a specific device. Let's say you're working on multiple GPUs and your model is on certain GPU and you want to move the data whole batch to the GPU. So the way we do it is in Torch, we have a function called to, which is part of tensor class. So if you specify the device name, it moves the whole tensor to that device. So if the tensor is already in the device, then it's no. So it's okay to call this even you're not sure. Okay, so now we have a batch class. Let's go to the next one. I wanted to show you how I visualize the training. So another useful tool I use is TQDM. Many of us may be already using it. If not, I strongly recommend using it. So what we do is instead of looping on data, we can give our data to this TQDM. It gives a progress bar. And as we consume the data from this iterator, the progress bar automatically gets updated. So as you can see, currently there's no training here, so it runs really fast. Let's see if I can run it. Oh, sorry, I was supposed to run these classes before I can. Sorry, this is a live demo. So this code works. So I just have to run it in the correct order. Log is not defined. Okay. Because I didn't run this. Okay. Okay, good. That runs. Okay, so now I think I should be able to show you the demo. So here is a progress bar. As we consume the data, it shows the progress. The key thing to note is it shows what is the ETA. So when is the training going to finish? So it's very helpful to know whether this experiment will be done before your next meeting or so. So TQDM is going to compute and tell you when it's going to finish. Also, you can add some extra information like what's the speed of how fast the training is going on, like how many images per second, or how many sentences per second, or tokens per second. I work on machine translation. For me, knowing tokens per second is really a useful measure to know if I make some changes, did it slow down my training or did it not? So here we can progress bar.set postfix and then set any information you want to set, and it will be updated in the progress bar. However, this is based on epochs. So there will be a separate progress bar for each epoch. So instead, now we can make one long progress bar by this function. What it does is it loops over all the epochs until I say, I want to train this model for 100,000 steps. Then it takes care of flattening the epochs into 100,000 steps. And now we have one big progress bar, as you see. So this estimate will be more reliable. So these slides will be shared, so you will have access to all these functions in case you want to use it. I'm just giving you an overview how to set up tools. That way you have some useful information, like when is this training going to finish, or what is the speed it is running. Okay, so this is number of batches per second, and this is number of tokens per second. Okay, so the next step is let's start with the trainer. So when we think of trainer, those are all some utilities to get to the trainer part. Now we are at the trainer. So here, trainer need a model, and it takes an optimizer, and it takes a loss function. So let's start filling these three details. To train a model, you need a model, you need an optimizer, you need a loss function, and you also need data set, which we already got. We got the data set. So for the trainer class, so one of the important function is you will have something called train function, which is a loop, right? So it takes training data loader, validation data loader, and it takes how many steps you want to train and how often do you like to take checkpoints. Usually, back in days, we took checkpoints once per epoch. But the new way we are doing is we are not going for epoch-based training. We are going for step-based training. We say train for 100,000 steps or 1 million steps, and then we say checkpoint every, say, 10,000 steps or 1,000 steps. So this loop, this is the same loop that I showed before. It has TQDM that gives us the progress, how long this training is going to take, right? And then we can also update some information like what is the speed. And then, so here is our place to take a checkpoint. Okay, so this is a template for training class, and we will start filling it one by one. But remember that now trainer also receives an argument called device. So on which device we want to train this. So it can be CPU, it can be GPU 1, 2, 3 if you have multiple GPUs. Okay, so I just received a question from Kushal. How do you manage between notebooks and Python files? What's your advice? Okay, so when I'm actively developing something, if I'm trying to visualize a graph, etc., I use notebooks. Let's say I'm actively playing with a function to see if I run this function, what happens. So in that case, I use notebooks. But once I am finalized, I just copy paste it to my Python file and place it in an IDE. So often I work on IDE. So there are two ways. One, we can use PyCharm IDE and use debugger in it. So we can look inside the variables like tensors. The other way is notebook. So especially when I'm looking for some visualization, I go for notebooks. Otherwise, I usually do IDE, PyCharm IDE. I hope that answered your question. Okay, so we have this training class set up. We have placeholders for everything, and now we need to fill these details. So, okay, so we don't have model yet. So let's start filling the model first. Unfortunately, I don't think I will be able to go in depth to the model. So I'm just gonna, let's look at model as a black box. We will see the internals of the models later. So I'm just importing it from a class called model. So again, so yeah, this will overwhelm you at this moment, but let's look at it as a black box. We have a function that gives us a model. Okay, so then we are able to fill this model. So we can focus on the engineering part, not the model architecture part. Okay, so we call this function and we get a model. Good. So the next thing to know about PyTorch is the model object has a nice string representation. So if you call log.info, or if you log this model, or if you print this model, it will give you a string representation. I'm sorry, I'm not sure why my notebook is so slow today. I'm running it live on a server, which it was supposed to print. Okay. So another question. So this string is only based on int. A better way to look at the model in TensorBoard. That is correct. So we will be seeing how to visualize model in TensorBoard soon. But I'm not sure why this is okay. Okay, because I didn't run it in order. I'm sorry. I should remember to run everything in order. Okay, so as you see, this is now working. Now if I run this, I get a model. And then if I run this, it should print the model, which it did not. Wow. Yes. So if I print the model, so we get this string representation in case you want to have a quick look at the model. So as I said, we're not go into detail of how to build a model at this time, but you can get a overview. Okay, we have something called embedding, then we have something called positional embedding, then we have transformer encoder that has multiple layers, 0, 1, 2. So we have 3-layer encoder. Then in the end, we have something called linear layer that takes this representation and project it to output space. This is number of classes. So this is a standard classifier, right? So, so I'm surprised why it is not printing it. Okay. So, okay, now we have, we made it till here. We have a model. So I just rewrote this function trainer as we will receive the model and then also receive the device. So how to move a model to the device. So your model may be on CPU, now you want to move it to the GPU. If this device argument says, I want to run it on GPU, then just move the model to the GPU. Then how to create an optimizer. So PyTorch has this and a torch.optim package. You can use Atom optimizer, or there are many other optimizers. In fact, let's see if I can quickly show you optimizers. So PyTorch has a lot of optimizers. So if you go inside Optim package, you see that there's a whole list of optimizers. There's Ada Delta, Ada Grad, Atom. So yes, there's almost every other popular optimizer out there. I'm just using Atom optimizer, and loss function I'm using cross entropy. Then learning rate scheduler, I don't think I will be able to demonstrate that in this talk. Okay, so now we have all the slots fill in. And now if we look at the training loop, I also updated the training loop, which is going to, it's the same training loop as before. It has TQDM to show the progress bar. Then we move the batch to the device, whichever the device specified in argument. So the code is portable. Then we supply these texts, lengths, and then output. Do we want raw probability? Do we want logics, or do we want probabilities, or do we want log probabilities? Remember, some of these loss functions takes logics, some of them takes log probabilities, some of them takes probability. So it's always good to reference the documentation, say cross entropy, and see what is it asking for. So this is another bug, because potential bug, because we assume we are giving probabilities, but what if the function is expecting just raw logits instead of, so, okay, let's go to cross entropy. It says input is expected to contain raw unnormalized scores for each class. So make sure you refer the documentation and be sure what kind of input is expected from your loss function. Here, if you pass, say, normalized scores or say probabilities or log probabilities, it's going to be bug, right? So that's why we are passing, I'm passing only raw probabilities. Sorry, raw score, which means logits. Then we give those scores to loss function. This is the same function as the cross entropy. So this function cross entropy takes input and weight. So it takes input and input and target. Weights are optional. Then it also has something called reduction equal reduction. Okay, so sorry, I think I should speed up because I wanted to show you the TensorBoard part. So yes, so we have a progress bar, and then at every checkpoint, we have another function called torch.noGrad. This is where it disables the gradients, because on validation, we don't want gradients. Using gradients, if you don't do this, it will still work. However, disabling gradients will save you a lot of memory and computation. So for validation, we don't need gradients. So we can, if you use bit block, it disables the gradients. Then, so another tip I want to share is, how do you know your model is bug-free? Okay, there are so many tensors, so many components. How do you know there are no bugs? So one thing you could do, an easy test, is take a small batch. A small batch can be as small as just one small data set, a data set as small as just one batch in it, and run your model on that one batch over, and see what happens. So if there are no obvious bugs, your code should overfit to your one batch that you picked. That means the loss should, if you run it long enough, the loss should become 0. That's when all the connections are proper, there are no bugs, there are no memory leaks. Sorry, this might not catch memory leak. That's another problem. So, but at least you would know that if the loss can become 0 on one batch, then the model is good. It can solve your data set. So here, as you see, the loss, if I run it long enough, the loss would eventually go to 0. Okay, so I'm going to interrupt it. Next thing is, if you want to look at the GPU utilization, as I said, there is a GPU stat command. It shows this is currently I just interrupted. So 0% CPU utilization, and I'm taking 2.5 GB of RAM so far for this model. So let's say I want to run it on CPU and see how fast it runs. Okay, so now I supply device equal to CPU, and you see the speed is 15,000 tokens, and it's going to take about 4.5 hours. Okay, I'm going to interrupt it. Okay, sorry, how do I clear this? So, okay, let's ignore that. So now if I run the same thing on GPU, you see the speed is now a lot faster, right? It's going to finish in 26 minutes. So now it's portable. It works on both CPU and GPU. And what you can do, other options is you can increase the batch size. Say I'm going to increase the batch size and monitor if you can, if we can fit even bigger batches. So with that, I still have a lot of memory left. It's really a small model. I'm training 128 dimension transformer. It's really, really small. But if I increase it to 1024, then probably it will exhaust all the memory. So in scenarios like this, the GPU is underutilized. What you can do is you can just increase the batch size. Sometimes if you have a bigger data set, and it would be, it would be easy to do it, right? But if you have a smaller data set, then this increasing the batch size to really a big value can be not so great. On small data set, again, if you already have a little data set, then you're not aiming for 100% GPU utilization. So, okay, so next section I want to cover is how to use TensorBoard, or how do I visualize the losses. Okay, so the good news is TensorBoard is now part of PyTorch. So if you can, so in PyTorch, you see this package called torch.utils.tensorboard, and there's a class called summary writer. So this summary writer class have this signature, like you can specify the directory where you can store the logs. And it gives you a lot of functions, like you can add a scalar value or a graph or an embedding or a text, image, video. So it has, almost all the MIME, all the types, all the MIME types. So how do you install TensorBoard? It's easy. You do pip install TensorBoard. So if you set up log directory at certain place, then you can visualize it by launching a TensorBoard server and passing this argument to the TensorBoard. So I'm going to show you how to do that. Okay, so what I did is I took the same trainer that I showed before. I modified few lines. Now you see I imported summary writer from utils.tensorboard package. I'm creating something called TensorBoard TBD with the summary writer class, and I'm passing the argument where to store the logs. So here, if you are working on experiment, it's best to put these logs inside an experiment directory. Okay, so it will be creating a directory called TensorBoard logs. So we have this object. Next thing is, let's say you want to visualize the model. So Kushal had asked, this can be visualized model. Is it better to visualize it in TensorBoard, right? Yes. So the issue or the difficulty with Torch is Torch models are dynamic graphs. So you don't have a graph until you run it, right? Unlike static graphs, you have a graph when you have created it. So we need to run something through the graph to get the graph. So what I'm doing is at step equal to 1, I'm giving a batch, and then I will be able to extract, add graph, tbd.addGraph, this model with these arguments. Now, these arguments will help us extract a graph from Torch model. So at step equal to 1, I give a batch and then I get a graph, and then TensorBoard will log it. Next is I can add a scalar. So if you look at these functions, almost all of them have something called global step, right? So you need to know on x-axis, it's best to visualize a step instead of epochs, because for this reason. So we can add a single scalar. So here, for every batch, I get a loss value. I can visualize the training loss, versus for every checkpoint, I get an average training loss and an average validation loss. So my validate function gives me validation loss. I can visualize a bunch of scalars. So now it's plural scalars. And then it takes a dictionary, and then I can say this is my training loss and this is my validation loss. Also, I can visualize embedding. So if you remember the model, so in the beginning, we had embedding matrix, the input is embedding, or even the classes also have embeddings. So we can visualize these scalars, embeddings. Again, you can visualize images, text, audio, video, everything. So let's start with this, okay? Going to run this, and I hope I have enough time to launch TensorBoard and show this. Or I'm not sure if it is. Okay, so this is a new trainer. I just ran it here, right? I'm going to run this. It gives you some warnings because there are some functions that are, there is a piece of the model where the graph it extracted is not proper, meaning that graph will change depending on your input. Okay, so that's the warning it is giving. Ignore it for now. Let's see if I can visualize TensorBoard. So if I look at this, there should be TensorBoard log. So I go for I go for TensorBoard log. Then I specify log directory equal to this and host equal to binding it to all the interfaces so I can access it remotely. On local laptop, you don't have to do that. Okay, so let's see. So, okay, remember, while it is launching, all we have to do is, first create a summary writer, which is available in TensorBoard package. Then use add scalar, scalars, graph, embeddings, video, or anything else you want to visualize to the TensorBoard. All of them will be stored under this directory. Okay. And now with this command line tool, we will be able, with this server we are launching, we should be able to visualize it. Okay, so it's running on this Saga machine. Sorry, let me close some of these. Oh, that's correct. Oh, I need to add .sci.edu. Right, so now we get TensorBoard. Nice. So what are we looking at? We added training loss, which was added for every checkpoint, right? If you remember, we added it for every checkpoint, and it varies a bit. So as you can see, it's more fine-grained. So it's, you can control the smoothing if you want to. Then also we added a bunch of scalars, 2 scalars to be specific. We added training loss, training checkpoint loss, and validation checkpoint loss. Those are visualized here. Correct. So these are added for every checkpoint, which was done at 1,000 steps apart. 1,000, 2,000, we have a data point. 3,000, we have a data point. So my recommendation is, again, TensorBoard tries to minimize the disk I/O. Try not to overwhelm the disk with too much logs. Okay. Then graphs. We also added a graph. So let's look at the model. You can zoom in.
Yeah, just we have a few more minutes here. So
okay, good.
Yeah.
So we have a class called text classifier. If you look at inside, you know, we have something called sequential, which we have embedding. Itself has embedding and positional embedding. We have a transformer encoder, which has multiple layers. Encoder layer 1, 2, 3. Then we have a linear layer, which is the last class projection, etc. So you can visualize it. You know, it works. All I did was just add that graph with pass one batch of an argument to extract the graph. Next, I also wanted to show you embeddings. It comes in projector tab. Embeddings are really heavy, so I'm only visualizing. If you look at this, I did a trick, which is embedding visualization is expensive because there can be too many embeddings. So I'm just picking the top 500, okay, to make this demo not hang. So what I'm doing here is we can see that let's say input embedding at step 5,000, and you have these options. Do you want to do TSNE or PCA? I think most of you may be already familiar with this, so I'm gonna just skip. So I also gave the labels to this, so I can stop. So you see, you can basically visualize embedding this way, or I don't know. Okay, so just wanted to say yes, this works. It's easy. All you have to do is add a few lines of your code. Then I only have a few minutes, so I'm gonna skip to, let's see. Maybe I should answer questions. I'm going to skip the rest of the part. I think I'll share the slides with you. So some of you asked, can you share your Slurm script? So yes, here's a link. These are some Slurm environment variables, Slurm arguments. And I take, so yeah, if you can look through this, sorry, I'll skip that part. And experiment. So the best practice is always set up experiments in a way you can share your experiments with others, and you can rerun your experiments later. So if you want me to show you one experiment, actually I have a bunch of experiments, show you one experiment, which is I have one central config file where it has everything about this experiment. What was the training data? What were the arguments? You know, training arguments, model arguments, optimizer arguments, and everything in one file. So anybody who wants to reproduce this experiment have everything they want to, you know, they need it. And so also I keep track of the Git commit, the latest Git commit, if anybody wants to, if you in the future wants to restore code to this particular commit, it's there. Okay, so Sorry, I think we are almost out of time.
Yeah. Well, thanks, TG. I think that was a really quick rundown on a whole bunch of stuff, but I feel there's a whole lot of things we could dive in deeper there. Maybe we can take. There's already one question on the chat.
Oh, sure. Yeah. So is it worth to set PyTorch up with Docker from Alex? Sure. I think using Conda would be more useful, more make your life easier than Docker, because if you have Conda, you can work with something like PyCharm IDE, for example, right? You have a Conda environment, you can say, PyCharm, here is my Conda environment, use this for debugging the code. But if Docker, I think it makes it a bit more complicated. But again, Docker was needed when installing CUDA, etc. was hard. Now Conda can install CUDA, etc. So just using Conda would be helpful.
All right. Well, is there any pressing question? One more we can take before we log off here. You could unmute yourself and talk. Otherwise, all right.
Okay. Thank you everyone for joining me today for discussion on PyTorch. And I will be sharing these this notebook. So in case you want to reuse this code or go through this one more time slowly, you will have it. I will share it on Slack channel.
Thank you, everyone. Thanks, TG.
Thank you.